Hello, welcome back. Today we're going to find the summation of cubes. What I mean cubes, the terms 1 to nth cube. So here I wrote the first terms, 1, 8, 27, and so on and so forth, all the way to the n cubed. Adding all of them up, what is that expression? And that is my goal. So let's get right to it. Let's write the first, let's say, 7 terms, 7 cubes. So this is 1 cube, 2 cube, 3 cube, 4 cube, so on and so forth. And this is 7th cube. So a pattern I found while I was playing around with this was the following. Upon computing the difference, let's say 8 minus 1, 7. 27 minus 8, 19. 64 minus 27, 37. 125 minus 64, 61. 216 minus 125, 91. And 343 minus 216 is 127. Alright, well, let's go further. Find the difference of the differences. So 19 minus 7 is 12. 37 minus 19 is 18. 61 minus 37 is 24. 91 minus 61 is 30. And 127 minus 91 is 36. Now, you can see that this looks like an arithmetic sequence. Indeed it is. Well, let's try to find the difference of the arithmetic sequence. Upon realizing that it is an arithmetic sequence, you should know that the differences should create a constant. And this constant, amazingly, 6, is actually what the power, in this case, we're interested in the summation of cubes, right? What's the cube? Third power, right? What's the 3 factorial? 6. Now that's a nice and surprising fact, but for now we won't be concentrating on this. Now once we stopped in this row right here, I want us to go one step that way. Now what I mean with that is, okay, you see how, for example, the number 18 is composed by adding 12 plus 6, and 24 is composed by adding 18 plus 6, and so on and so forth. 18 can be composed by subtracting 6 from 24. Well, let's do it one more time. So let's subtract 6 from 12 in order to get 6. And let's subtract 6 from 7 in order to get 1. Alright? Well, using the following tree, let's actually start to find any patterns. Now, the idea of using this tree is when breaking sums into smaller bits, we can often find many patterns. In this case, let's try to write, let's say, simple numbers. 27. Now, when I mean write, let's write it in simpler terms. For example, 27 is composed of, alright, we can start out at 1, and then when we add 7, we get 8. We're almost there. Now we just have to add 19. But another way of writing 19 would be doing the following. 19 is composed, according to this chart that we've done, of 7 plus 12. So we can simplify to that. And the following will give us 27. But now, remember we've expanded this row right here? Well, we did this for a reason. In order to be as simple as possible. The 7 can be split up into what? 1 plus 6. The 7 right here can also be split into 1 plus 6. And the 12 can be split up into, well, 6 plus 6. Right? Alright. Now, when I first saw this, I thought it was just a coincidence. But in reorganizing it in a very efficient manner, it was not. I will draw it in a geometric shape. So, in a pyramid-like shape, I will write it as 1. 1 plus 6, you see? Here I wrote the first row. Here's the second row. This is the third row I'm going to write right here. 1 plus 6 plus 6 plus 6. Yep. Now, at first, this might look like it has no pattern whatsoever, but let's keep on. Let's choose some other number so we can see this is not just a coincidence, although you might not see it now. Let's write some other number and expand it out. Well, in this case, I'll choose 64. Alright, well, let's do the same process. We're going to expand 64 into something such as the following. 1 plus 7 in order to get 8 right there. And then in order to get 27, we need 19, just like the previous problem. But 19 is composed of 7 plus 12. Right? This was 19. Okay, so we're at 27 now. But we want to get to 64. We want to write 64 in a new way. What do we need? We need to add a 37. But 37 can be written in a simpler version. It can be rewritten as 7 plus 12 plus 18. And now, just like we did last time, let's simplify this 7 into terms of 1 and 6. So 7 splits up into 1 plus 6. This is 7, same thing, 1 plus 6. I'll separate them through parentheses. 12 separates into 6 plus 6. 7 into 6 plus 1. 1 plus 6, same thing. 12 into 6 plus 6. And 18 into 3 sixes. Now, please don't lose orientation here. All I'm doing is I'm trying to make these numbers into simpler form so we can see some geometric pattern, and I will show you what I mean with this pattern. Now let's try to write this in a geometric fashion. So here, just like last time, I'll write 1 for this number, then 1 plus 6 for here, then I'll write 1 plus 6 plus 6 plus 6, these 3 sixes, representing the 19. And then representing the 37, I'll write 1 plus 6, and then all the 6s remaining. 1, 2, 3, 4, 5, 6. 6 sixes. So 1, 2, 3, 4, 5, 6. Now, let's compare. The pattern right here that we just wrote out, it's representative of 64. The pattern up here that we wrote previously is a pattern of 27. But what pattern is there? Well, look at the 6s. We can actually look at the 6 like this. We can think about it as a rectangle like this, and then as a horizontal rectangle like this. Well, that may not look like it has any significance, but let's try to 64. This is why we expanded the 64th term, because we have a rectangle of 6s like this, and then we have a square, and then a horizontal rectangle of 6. Now, what does this mean? This means that if we think terms about a rectangle has a base and a height, right? Well, in this case, look at we're going to be talking about the 64 version. In the first rectangle that we drawn, there's 3 6s. 3 heights of 6s and 1 length of 6, if you will. And then in the next one, there's 2 heights of 6s and but then the extension grows to 2 lengths of 6. As you see there, 2 6s, 2 6s up. And now when we think about the last one, there's only 1 height of 6, but actually 3 extensions of 6. And this pattern actually continues as long as you keep on expanding. So we can actually take advantage of this. In this new paper, I'll show you. So, if 64 can be rewritten in this very elegant fashion, and 27 actually follows this pattern, actually let me show you 27, right here. You see how there's a height of 2 and then a length of 1, but then the height goes down by 1 and then the length increases by 1. So, what I mean, the height goes back to 1 and the length actually increases by 2. So we can actually think about this as area of 6s. So let's actually try to compute this. So we were interested at first of the 64 version, and let's actually go. So let's see. This pyramid looking thing, or this triangle of 1s and 6s, represents 64. And now previous numbers such as of cubes such as 32, 8 and 1, they were all composed of 1s and 6s, and we can actually show this. So for the 64, we see that we have how many 1s? 1, 2, 3, 4. 4 1s, and 64 is the 4th term. So I can write n representing the amount of 1s in the 64th term, right? So that's for the 1s. And representing the 6s, we have n minus 1 terms. Because remember, 64, right here, is the fourth term, right? And because it is the fourth term, we can actually see that. Oh yeah, okay. So here, there are 3 6's, and 3 is less than 4 by 1, right? So it's going to be n minus 1 6's, right? And then we see the square right here. It'll be n minus 2 6's, because we have just, instead of 3 6's, we have 2 6's. 4 minus 2 is 2 heights of 6's. So we write 6 right here. But then the length of 6 is 2. So this I'll write as height. This as length. Right? And then in the ladder, the same thing happens. N minus 3, because we had 4. This is the fourth term, right? 4 minus 3 is 1. So we only have 1 height of 6. And the length increases to 3. 1, 2, 3. Right? So same thing here, height, length. Alright, so this, I wrote it out only for the 64 term, right? But remember, the same thing happens for all the other terms. So, for example, here we have n amount of 1's, right? So in this case, 4 amount of 1's. And then we have, the term before, 3 amount of 1's, 2 amount of 1's, so on and so forth. So if we've had something like this, and we're talking about 1's now, 1 plus 2 plus 3 plus 4 and so on and so forth. This addition is an arithmetic series addition, and we can simplify as n plus 1 divided by 2. Now, okay, now this summation right here is a summation for all numbers up to a certain amount of n, and this is only we're talking about in terms of 1. Now, for the terms of 6's, it becomes a little bit complicated, but not that complicated. Let's actually think about this. So, right here, we have n minus 1 amount of 6's, right? So in this case we have 4. We have how many? 3 6's, right? And then previously we have 2 6's, counting for the 27th term. And then we'll have 1 6's, right? And so on and so forth. And if you don't know what I mean, I'll show you what I did for the 20. Remember, for the 27th. How many 6's do we have in this height? We have 2. In the fourth term, we have 3. So it'll be safe to say that right here we have n minus 1, and then for the 27, n minus 2, and so on and so forth. So this is just a summation, n plus 1 divided by 2. But remember, n minus 1 term. So for wherever we see n, we're going to substitute n minus 1. So that's n minus 1. We're going to substitute in there n minus 1, n minus 1 plus 1 is just n divided by 2, and then of course times 6 right there. Simplify that in a jiffy. And we can see the same thing happening here. We just have one less term of 6, n minus 2, so on and so forth. So we're going to do the summation n plus 1 divided by 2. And we're going to substitute n minus 2 for wherever we see n minus 2, n minus 1 divided by 2 times 6. And in this case, we have a times 2 right there, that length. And now we'll take care of that soon. Just wait. And then we have right here 6n minus 3, same idea. We're going to write 6, the summation. n plus 1 divided by 2 was the substitution of n minus 3. n minus 3, n minus 2 divided by 2. And then of course times 3 right there. Alright? So for now, let's forget about the 1's. It's pretty much solved, but let's think about the 6's right here. We can actually represent this using sigma notation. Sigma notation makes things much more easier because it substitutes things for us immediately in an arithmetic order or fashion. So what do I mean? So let's actually write a sigma. Sigma I equals 1 to the n. Now we're going to represent here, everything after the 1. All the 6's, we're going to represent these additions, because remember, we're going to have to add this one, this one, this one, and the next one, and the next one, and that will take into account the 6's, and that is what we want. So let's actually do that. So right here, we're actually going to simplify. 6 divided by 2 is always 3 for all of them. See how there's always going to be a 3 there. And now this number we're going to take into account right now. So we're going to write 3, because all of them look like they have a 3. Then we're going to write n minus I. Now, why did I just do n minus I? Because if you see right here, n minus I will take into account the first one, and so on and so forth, because when we plug in I equals 1, which will be our first term, n minus 1 is right there. Then the next term, n minus 2, and n minus 3, and so on and so forth. And then for the next one, it starts at n. So, and each one of them start decreasing. So it is appropriate to write plus 1 minus I. Now I do this to so it can start healthy at n and then start subtracting. For example, plug in I equals 1 right there for the I. That'll be n plus 1 minus 1, which is just n. Then plug in I equals 2. N plus 1 minus 2 is just n minus 1, just like we see there. Alright? And then for this term right here, do you see how this coefficient's 2, which represented here the length? Okay, sorry, you can't see that. Here's the length right there. Remember, these coefficients, the latter coefficients represent the length. Well, let's actually take them into account right now. Here, there is no coefficient, but because it's 1. Here, so I'll circle them. Here's 2, and here's 3. So you see, they all start increasing by 1. We can represent this by the variable I. So in the first one, I equals 1, I equals 2, I equals 3, and so on and so forth. So here, theoretically, so far, this is the same thing as all of these additions. So now, the only problem we have is just expanding this, and using simple algebra, this should be done in a jiffy. So let's actually start. Okay, so let's actually start. Right here, we immediately see one of our properties. We can take out the coefficient. We have n minus I, n plus 1 minus I times I. Let's actually expand the I right here. This is simple. Ni minus I squared. And then we're going to have to multiply times this. Just going to expand through. That's n squared I. Then that's plus ni minus ni squared, right? Then right here, minus ni squared. We're just expanding it. Like, we're right there right now. Minus ni squared, and then minus I squared. And finally, plus I cubed. Let's actually simplify things right now. So here we have n squared I, that's single. Ni, that's also single. And then we have a minus ni squared minus ni squared. That can be simplified. Minus 2ni squared minus I squared plus I cubed. And of course we have the sigma right here. And although you think we can't simplify any further, there's one important thing that will save us time. Remember, technically these n's are actually constants. The only variable here that we have is the I. So let's group the correspondent variables by themselves. So here we have I to the first power. Let's factor out whatever terms, coefficients we had. Alright. Then right here we have to the second power. Let's factor out an I squared. Here we have 2n plus 1. And of course here we have the I cubed. Remember, sigma I cubed is what we're looking for. We can't actually touch this, otherwise it will be a circular proof. So we have the sigma. I'm not going to write the intricacies right now. So now it's time to expand. These constants can be taken out, and then we can actually go in immediately. So I'll start right now. So for the first term, remember, sigma can distribute, right? So let's actually start. N squared plus n sigma I, okay? And then right here the same thing, minus 2n plus 1 sigma I squared. And then right here we have plus sigma I cubed. Remember, when I touch this is what we're actually looking for. We'll leave it alone for now. And let's actually concentrate on these right here. So let's go ahead and simplify using the respective sigma terms. So sigma I, and this is just arithmetic sequence. You should be able to identify it at this level. Sigma I is just n plus 1 divided by 2. Okay, and we have n squared plus n right here. Remember, we're about to multiply together. Just wait. And right here that's negative 2n minus 1. Okay, remember there's an addition right there. I just expanded the negative notation. Sigma I squared is what? That's just n plus 1, 2n plus 1 divided by 6. Okay, plus sigma I cubed. You don't want to touch sigma I cubed, for if you do, it will cause a circular proof. Let's expand the numerator on the top right here. That's n squared plus n squared plus n. Okay, let's go ahead and simplify. N to the 4th power plus 2n to the 3rd plus n squared. Okay, and this divided by, of course, divided by 2. And then now we're going to have to simplify this much longer part, although it's not impossible. Here, this is just, I'm doing step by step, n times n minus n times n plus 1. It's n squared plus n, okay, times the 2n part, the 2n part. That gives us 2n cubed plus n squared plus 2n squared plus n, okay. Simplify things together, 2n cubed plus 3n squared plus n. Alright, now we're missing the times negative 2n minus 1. Let's go ahead and take that into account. Almost done. This is the last major step, and then everything will be much easier from now on. That's negative 4n to the 4th power, 2n cubed times negative 1, negative 2n cubed, minus 6n to the 3rd power, minus 3n squared, minus 2n squared, and of course minus n. Let's simplify things together. Negative 4n to the 4th power, negative 8 to the n cubed, negative 5 to the n squared, minus n. Okay, almost done. Everything, remember, we had a 6 in the bottom. Okay, and this we're going to have to add it to n to the 4th plus 2n cubed plus n squared divided by 2. Okay, almost done. Don't lose track. So here we're going to need a common denominator. Let's multiply 3 in the numerator, 3 in the denominator. This gives us 6. Everything times 3. 3 times 2 is 6. Here 3. Let's add things up now. Cross the bridge. Negative n to the 4th. That's 6n cubed. Negative 2n cubed. Negative 2n squared. Minus n. All of it divided by 6. We're not done. Remember this lost sigma I cube? If you can see it right there. Well, let's not touch it, but let's keep track of it. Remember, this will have to be, we're gonna have to add right here sigma I cube. We need common denominator and numerator, so plus 6 sigma I cube right there. You see, we're not touching it, I'm just keeping it there. And now remember, that is completely simplified, but we have to multiply it times 3. If you recall, we expanded this right here, and we extracted out a 3. Well, let's actually take that into account. The whole thing, multiply times 3. Well, right here, the denominator cancels out. The denominator now becomes 2. So, this whole chunk, this whole sigma, is now simplified. Right here. Now, remember, we took into account the 1's right here, using n plus 1 divided by 2. We told you just to forget about it. Well, now we're going to have to add it to this. It's just this and that, and we're almost done. So, let's actually go for it. So remember that the 1's were represented with n plus 1 divided by 2. And the formula we just got was, we're going to have to add it right there, plus negative n to the 4th minus 2n cubed minus 2n squared minus n plus 6 sigma I cubed, and all of it divided by 2, remember? Right there. And let's add these things together. Okay, n times n plus 1, that's just n squared plus n. Okay, so right here we have negative n to the 4th power. Right here the n squared becomes negative, but first let's write the cube. Minus n squared, the n's cancel out because n minus n is just 0, plus 6 sigma I cubed. Okay, let's stop. What we have right here is the addition of, remember, all these terms. Remember, we had the 1's term, and then the sigma took into account all of the terms after 1. Well, that's this thing right here. So this is actually our answer. And what is our answer? The first thing we were looking for in the first place was sigma I cubed, right? Remember, that's why I told you not to touch it, so it doesn't become part of the proof. Okay, so it doesn't taint it. So let's actually put the sigma I cube into one side. Okay, so let's multiply times 2. 2 cancels out. 2 is right there, right? We're going to subtract minus 6 sigma I cube. And that leaves us with negative 4 sigma I cube. Your heart should be racing right now. We're almost done. And you should be predicting the next steps already. Divide both sides times negative. Everything becomes positive. Divide by 4. And sigma I cubed equals n to the 4th plus 2n cubed plus n squared divided by 4. Let's simplify if you don't recognize this. There's a common term of n squared. Factor it out. N squared plus 2n plus 1 divided by 4. Still not familiar? This right here can be simplified to n plus 1 squared. We have the n squared, and we get the 4. Ta-da! That's the proof. This is actually where the sigma I cube comes from. And I just got this from playing around with numbers. Oh, thank you. Subscribe!